Hello, my name is Anthony, and this is my Lab 2 report. So we know that most objects gain a charge when rubbed or pulled apart, but how much? So the purpose of this experiment is to determine how charged a piece of tape becomes from doing so. In this experiment, I charged pieces of tape by sticking and ripping them from a surface. Then, using the principles that opposite charges attract and like charges repel, that the net force on an object is zero when it is not accelerating, and that the main vertical forces on the tape were the gravitational and electric forces, I was able to use a code to calculate the charge to be 4.045 times 10 to the negative 9 coulombs. The model code uses two basic assumptions, that there is no air resistance because this has a minute effect in real life, and that the tapes have the same charge evenly distributed throughout the length of the tapes, and this is because the tapes are uniform and identical. Using the second assumption, the model represents the charged tape as a line of charged particles, and uses this to calculate its electric field and force. It also calculates gravity using the definition force equals mass times gravity due to acceleration. For this experiment, I used 3 tapes with the dimensions shown at the top. I stuck the first one to the table to be used as the surface. The next 2 I stuck on top of the first and then ripped off to make them charged. When the 2 tapes were close to each other, they repelled, which makes sense because they have the same charge, and same charges repel. Also, then, I grabbed a plastic pen and rubbed it through my hair to give it a negative charge. I found that the tape was attracted to this, so that means that the tape has a positive charge because opposite charges attract. To obtain the magnitude of the charge, I use a setup like on the right. The system is tape B and the surroundings are tape A and the Earth. The assumptions are that both tapes have the same net charge since they were charged the same way, and that the tapes can be treated as lines of point charges, which was explained earlier. I made the setup by placing tape B between 2 books so that it was hanging, and then placing tape A below tape B and moving tape A closer to tape B until tape B began to float. At this point, I recorded the distance between the 2 tapes to be 2 centimeters. When the upper tape was floating, the 2 vertical forces acting on it were the gravitational and electric forces, as shown in the free body diagram. Since the tapes have the same charge, the lower tape caused an upward force on the upper tape, so it floated. And when the upper tape was floating, it had 0 acceleration, which meant its net force was 0. This meant that the 2 forces on that charge must be equal in magnitude, which is shown in the equation at the bottom. The code is used to calculate the charge of one of the tapes, and the link for it is in the description. The first few lines of the code introduce the initial conditions as shown on the slide, and the next few lines introduce the mass and charge of one of the tapes. Then, the E-field function determines the electric field given a charged particle and the observation location. And next, the line charge function creates 2 lines of spheres 2 centimeters apart, which models the experiment when the top tape began to float. Then, some scales are introduced to ensure all vectors can be seen. The next part calculates the total electric field each top charge experiences by superposing the electric fields from each of the bottom charges. These are the green arrows. The electric fields of each of the top charges are then multiplied by the top tape's charge to get their net electric forces, and these are then superposed to determine the top charge's total net electric force, which is the white vector. The code then finds the top tape's gravitational force by multiplying the tape's mass by g. This is the yellow vector. It then prints out the magnitudes of the tape's gravitational and electric forces. I found the charge of the tape to be 4.045 times 10 to the negative 9 coulombs because this is the value of the charge, which makes the gravitational and electric forces equal, which has to be the case as determined in the experiment. If I modeled the tapes like in Lab 1, I would have found the charge of the tape to be 1.67 times 10 to the negative 8 coulombs. This is about 5 times larger than the Lab 2 value, but both estimates are pretty close together. The reason for this difference comes down to the models. Both labs calculated the charge by having the net force on the top tape equal 0 and then setting the gravitational force equal to the electric force. Both labs also assumed that the tapes had equal charge. However, Lab 1 modeled the tapes as point charges at the tape's center of mass, while Lab 2 modeled the tapes as lines of point charges. Therefore, the Lab 2 value is closer to the actual value, because the real value is found by calculating the effect that each electron in the bottom tape has on each electron in the top tape, and the Lab 2 model is closer to the real-world model. The experiment also likely had error. This was partially due to human error from measuring the length of the tapes and the distance between the tapes when tape B was floating, but also due to the charge of the tape wearing off quickly and me having to touch the tapes with my hands, which caused the tapes to lose charge. In conclusion, the purpose of this lab was to determine how charged a piece of tape becomes after being stuck and ripped from a surface. I charged the tapes and determined they had a positive charge because they were attracted to a negatively charged pen. To find the magnitude of the tapes, I found the distance between the 2 tapes when the lower tape caused the upper tape to float. and when floating, the net force equaled 0 on the top tape, which meant its gravitational force equaled its electric force. Using a code model to represent the tapes as lines of point charges, I found the charge of the tapes to be 4.045 times 10 to the negative 9 coulombs. This value was similar but more accurate than the Lab 1 value because the model was more accurate. However, there were still some errors, but overall the experiment found a good estimate for the charge of the tape.